Hello. I also we will wait till 6:05 and after that I will class the start. Let's start the class. Vinay, Vinay, class started. Hello all. So it's 6:05 p.m. now, and I will start the class now. So first of all, I'd like to introduce myself. So my name is Manoj Shikhar. I'm a PMRF scholar at IIT Delhi. I'm working in the Department of Applied Mechanics, and I've done my BTech and MTech from IIT Kharagpur. And I will take this live session on every Tuesday from 6 to 8 p.m. Now, before starting anything, I'd like to declare one thing that on PMRF portal, oh sorry, on Swayam portal, you have some weekly questions, assignments. We are not supposed to help you with those assignments. If you have some assignment due below, please do not ask any question from that because we are not allowed to help you. Apart from that, this is week 7 of the live session. And in week 7, the topics which were covered in the video lectures are linear momentum balance in cylindrical coordinate system and strain matrix in the cylindrical coordinate system. So we will first recapitulate about few concepts like what is cylindrical coordinate system and how to write LMB and strain matrix there. And for the notes of this course, Solid Mechanics, you can visit this website of Professor Ajit Kumar, the instructor of this course. And from there, you can download PDFs. In those PDFs, at the end, you will have some questionnaire. Those questionnaire will have questions which are similar to questions which are asked in the competitive exams. So if you solve those problems, it will be useful for you. And I also, as you may have seen in my previous lectures, I also take up those questions. I solve some of them. I leave some of them for you. So let's begin the session. Okay, one more thing. Earlier I used to write in OneNote, but now I will be using Windows Journal. So you might find that interface has slightly changed. So in cylindrical coordinate system, first thing to remember, our bases are ER, E theta, and EZ. Okay. So this is a generic cylinder. Till now, maybe you may have read about cylinder which had a fixed radius throughout its length, but a generic cylinder may have different radius values in uh, alongside its length. So suppose at some point this is R. So at any, suppose how do I write this point? So the coordinate of this point will be r, theta, and z. So here we take a circle. Suppose this is our origin. So from here, the height is z. If I draw this circle, I hope I'm audible to all of you. Am I audible to all of you? My mic is on. So anyways, so in this, the basis ER is in the radial direction and E theta is taken at 90 degrees from ER. So this is the direction of E theta. So suppose if I take this point here, the direction of ER will be this, and this will be the direction of E theta. And EZ will be in the direction of positive Z. So this is the direction of EZ. Things to keep in mind. ER and E theta change with change in point. If you do further analysis, you will realize that ER and E theta vary only based on theta. With respect to theta only. This means that ER is a function of theta and E theta is also a function of theta. So this you should keep in mind. And EZ vector, this remains. So these are three things you should keep in mind. That ER and E theta will change with change in point. ER and E theta vary with respect to theta only. Means that if I move in the radial direction here, suppose if I choose this point or I choose this point, here our ER and E theta will be same because this will be ER, this will be E theta. So only when we move along theta direction, then only ER and E theta will be different. This is what we mean. That's why they are the function of theta only. Now, how do we take the element of a cylindrical system? Okay. So suppose this is our cylinder. I'm drawing a general cylinder. That's why the radius is not same along all the directions. So if you take a small element, it will look something like this. So in zoomed view, it will look something like this. This is positive Z plane. This is negative R plane. Sir has discussed all these already, so I will just uh, skim through the concepts. This is minus theta plane. Just boost your memory. Refresh your memory. I'm showing this. Okay. So as usual, uh, you can write traction on various planes. These have been already covered in the video lecture, so I'm just writing the steps can be found. Then you can do the you can find total body force. And we can do the Taylor's expansion. And if we do the force balance, we shall get our equilibrium equation. Efficiency cylindrical coordinates. Okay. One thing to keep in mind, generally in rectangular coordinate system, rectangular Cartesian coordinate system. E1, E2, E3, they were constant. So their differentiation with respect to other coordinates was 0. But in cylindrical coordinate system, derivatives of ER and E theta with respect to theta will not be 0. Okay. So in cylindrical coordinate system, that derivatives of ER and E theta will not be 0 when we differentiate with respect to theta. So what are the values of these? So if you do the calculation, you will get the following result. Del ER by del theta is E theta, and del E theta by del theta is minus ER. Okay. So this was about the direction, and now I will directly write the final equations we have. If any one of you has any doubt, you can write in the chat. If you are not able to hear me, not able to see the screen, you can write in the chat. So we have three different directions, R, theta, and Z, and we have three different equations. So in R direction, we have del sigma RR by del R plus 1 by R del tau R theta. You will see that most of the terms will follow the similar pattern, what they did in the Cartesian coordinate system. So there is one extra term in the RR direction, which is sigma RR minus sigma theta theta by R. This is the extra term you can see. And one more thing you remember for cylindrical coordinate system or any coordinate system where there is an involvement of theta or phi, something like that. Whenever you will have a derivative, you will see that it is getting accompanied by 1 by R. The reason being, we are differentiating the quantity with respect to length, and theta does not have any unit. So therefore, every time it will appear with 1 by r. You will see this a lot in the cylindrical coordinate system or in a spherical coordinate system also. You will see this. Here also you see sigma r minus sigma theta has the unit of pressure, that is Pascal, and r is length. So Pascal by length. Here also see the differentiation of a stress component with respect to z, Pascal by length. And we have the body force per unit volume Br equal to rho into Ar. Acceleration, sorry, this is a component equation, so there will not be any bar which I wrote there. In theta direction, personally I prefer to write sigma r theta, sigma r z, but since sir has followed this tau convention for shear stress, I'm writing tau there. So if sometimes I write sigma r theta, it is nothing but tau r theta only. See, we are writing in the theta direction. That's why the first term is theta, theta, theta. Here we were writing in r direction, so the first index was r, r, r. Though later on we will see that these components are symmetric anyway, so it won't matter much. But just to remember that the direction in which we are writing, that index will come first. Did someone have any doubt? I thought I heard something. Okay. In z direction, tau zr by del r plus 1 by r tau z theta del theta plus sigma zz del z plus tau zr by r plus bz equal to rho az. So these are the equilibrium equations in three directions, r, theta, and z. And we will see how to use them. Now the other topic was strain matrix in the cylindrical coordinate system. Let me change the color of. Strain matrix in cylindrical coordinate system. Strain matrix in cylindrical coordinate system. Okay, so the definition of strain matrix was 1 by 2 gradient of u plus gradient of u transpose. So this is how we had calculated the strain matrix, right, in Cartesian coordinate system. This formula will be same for cylindrical coordinate system. So basically, we should know how to find the gradient of u in a coordinate system. Suppose if tomorrow I give you that find the strain matrix in uh, spherical coordinate system, then if you know how to calculate gradient of a function or gradient of a vector in a spherical coordinate system, you will be able to write a strain matrix. Okay. So gradient of any quantity is defined as, so this is the definition. Okay. This is how the gradient is being defined. So this is the definition of gradient. Now, since we are dealing with the cylindrical coordinate system, our u vector we write in cylindrical coordinate system. Okay, so u r here plus u theta e theta plus u z e z. Displacement along radial direction, displacement along circumferential direction, displacement along z direction, also known as the length direction. Okay, you can say the height, whatever you prefer. So long radial direction. Okay, so these are the displacements along radial direction, the circumferential direction, and z direction. And one thing to remember is UR can be a function of r theta z. U theta can be a function of r theta z, and uz also can be a function of r theta z. Okay, so these can be functions of r theta z. So if we want to calculate the gradient of u, what we will do? Here we will replace by u. So u is our now. One thing you should remember is that er, e theta, and ez, they are not dependent upon r. Okay, so differentiation with respect to r will be simple. But when we differentiate with respect to theta, we also need to differentiate er and e theta. Okay, because they depend upon theta. So this thing you should keep in mind. So these two terms, they are pretty straightforward. Okay. Here we will just differentiate UR with respect to R and so on. So I will write it directly here. Okay. Here we need to apply the product rule of differentiation. So the first term will be 1 by R del UR del R here. Sorry, it should be del theta. Del R. Maybe I should write this in a new line, because this will take a lot of space plus 1 by R del UR del theta ER plus UR del ER del theta plus del U theta del theta d theta plus U theta del E theta del theta plus del UZ by del Z EZ. This is dyadic with p theta. EZ was independent of theta, that's why it was not differentiated with respect to theta, plus the third term here, it should be del Z, not del R. Sorry for the mistake. Okay. So we can replace this by E theta. This can be replaced by E theta. And this can be replaced by minus E, right? So basically, now we have all the terms of this tensor, and we can write this in a matrix form. I will show you what is the matrix form, and then if we apply this formula of strain, we can get the strain matrix. So I will directly write the strain matrix here. The matrix representation of a strain tensor here. Okay. Maybe I should write the how do we fill the U tensor also. So gradient of U tensor, so that it will be easier for you to follow. So to fill gradient of U tensor, write R theta Z. Here write R theta Z. Okay. So the first part, this decides the row in which this term will go, and the second part decides the column. So both are RR. So the first column will be filled by ER, dyadic ER. So it is del UR by del R. E theta and ER will go where? They will go to second row, the theta row, and RH column for R. So here it should be del U theta by del R. Okay. Anyways, and del U by where is it? It did a mistake here. It should be del U Z by del R. So here del uz by del r will go into this. Okay. Similarly, if I want to fill the theta column, wherever theta is coming after this dyadic sign, that will be filled using theta column. So for the ER dyadic E theta, this means that row of R and column of theta. So here it should be 1 by R del UR by del theta minus UR. Okay. Sorry, minus U theta, not UR. This is ER. Here we have minus here. So this will be how it should be filled. Now for the theta row and theta column, we have UR E theta and del U theta E theta. So it should be 1 by R UR plus del U theta upon del theta. And for the last column, we have del U Z upon del theta. Why am I making this mistake again and again? So here it will be del U Z del theta, and there will be 1 by R multiplied here. Okay. Similarly, you can fill the third column. So for filling the third column, what will you will have? You will have del UR del Z. Then you will have del U theta del Z. And the last but not least will be del U Z del Z. Okay. So this is the U matrix you have. Now for epsilon you can do, and you can see that the U matrix is not symmetric. This is not symmetric. So epsilon is 1 by 2 gradient of U plus gradient of U transpose. So you just substitute this here, and you will get the final result. So the final epsilon matrix in the matrix form will be del UR by del R 1 by 2 1 by R del UR by del theta minus U theta plus del U theta del R. Here it will be 1 by 2 del UR del Z plus del UZ del R. Okay. Then here this will be the same value will be here. Okay. Here you will have 1 by r del u theta del theta plus ur. Here you will have 1 by 2 del u theta del z plus 1 by r del u z del theta. So we have simply put this gradient of u here and we are finding what are the components. Nothing very fancy. Just to complete the discussion, I'm writing this matrix here. So this is the matrix representation of strain tensor in cylindrical coordinate system. Okay. Now one more thing, just to mention, stress strain relationship. For isotropic material. Okay. So now what is the characteristic of isotropic material? In isotropic material, you will get the same value of the properties along any direction you move. So at a point, it does not matter in which direction you are moving, you will encounter the same value of the property. So if you're working with E1, E2, E3 coordinate system of rectangular coordinate system, or you're working with ER, E theta, EZ coordinate system, as long as we have three mutually perpendicular coordinate systems, sorry, three mutually perpendicular axis, we don't like the relation between the stress and strain will not change. Okay. So here also ER, E theta and EZ, they are mutually perpendicular to each other. E1, E2, E3 were also perpendicular to each other. So the relations between stress and strain for an isotropic material will remain the same. So if I want to write sigma RR, or let's say if we want to write epsilon RR, okay. So we will write it as 1 by E sigma RR minus nu sigma theta theta plus sigma ZZ. Okay. Okay. Similarly, if you want to write epsilon theta theta, it should be 1 by E sigma theta theta minus mu sigma ZZ plus sigma RR. Epsilon ZZ will be 1 by E sigma ZZ minus nu sigma RR plus sigma theta theta. Now with the shear part, so if I want to write tau r theta, it will be G times 2 times epsilon r theta. So epsilon, what will be, so 2 times epsilon r theta is our gamma r theta. So if we want to write gamma r theta, it will be tau r theta divided by G. Similarly, if I want to write gamma rz, it will be tau rz by g. And I really have a bad habit of mixing r's. Okay. Because I'm writing gamma here, that's why I'm changing the r to cursive r. If I want to write tau z theta, it will be tau z theta upon g. So this is what has been discussed in previous week or in week 7 lectures. Now we will move on to to solve some problems. So we have a question here, question number 7. The deformation of a body is such that it follows the following displacement field. U r equal to 0.5 r square plus 0.2 theta, u theta equal to 0.4 r theta, and uz equal to 0.02 plus 0.03 z square theta. What is the circumferential strain? So though they have asked about circumferential strain, let's find out other strains also. Okay, just for the sake of practice, we will find other strains also. So I will write the question in. So they have given you r equal to 0.05 r square plus 0.2 theta. Okay. They've given you u theta equal to 0.4 theta. So u theta only depends upon theta in this question. This is 0.4 theta. And uz is 0.02 z into 0.03 z square r. Let me just check if I have written the correct form. 0.05 r square, 0.2 theta, 0.4 theta, and 0.02 z into 0.03 z square. So they have asked about circumferential strain. So what is the circumferential strain? Circumferential strain is epsilon theta theta. They want you to find epsilon theta theta. But let's find other values. So we will use this formula like so this is our epsilon RR. Maybe I will write it here. This is epsilon RR. This is epsilon theta theta. This is epsilon ZZ. Okay. This is epsilon R theta. Epsilon R Z. And this is epsilon Z theta. Okay. So we will use these 6 formula to find out what is the value of strains. So first is this. So epsilon R is what? Del U R upon del R. So this will be what? 0.05 into 2 R. 0.1 R. Epsilon theta theta is what? 1 by R del U theta by del theta plus UR. So you will do what? 1 by R. Differentiation of U theta with respect to theta is 0.4 plus 0.05 R square plus 0.2 theta. So this is your so this is what they had asked for. Let's see if this is the option. There. 1 by r 0.4, 0.05 r square plus 0.2. So option B was correct in this case. Sorry, option C was correct, not B. Option C was correct. But let's find other components. So epsilon zz is del uz upon del z. So if we differentiate uz with respect to z, we will get 0.02 plus from here we will get a factor of 2. So it will be 0.06 zr. Now I got off diagonal. So suppose if they tell you what is the shear strain, like what is gamma r theta, okay? So you will have to multiply this epsilon r theta by 2. Remember to multiply this factor of 2. Otherwise you will get epsilon r theta. Epsilon r theta and gamma r theta are two different things. So first we'll calculate epsilon r theta. It will be 1 by 2. So substitute the values here. So 1 by 2 into 1 by r. Del u r by del theta will be 0.2 minus 0.4 theta plus del u theta by del r is 0 in this case. So our final will be 1 by 2 r 0.2. Maybe I will divide. It's because we can cancel 2 here. So 1 by r 0.1 minus 0.2 theta. This is epsilon r theta. Now what will be gamma r theta? This will be 2 times epsilon r theta. Okay. So the answer will be 1 by r 0.2 minus 0.4 theta. So del u r by del z is 0 because u r is not depending upon del z. Del u z by del r is 0.03 z square. So this is our epsilon rz. What will be gamma rz? This will be 2 times epsilon rz. So 0.03 z square. Okay. Last but not the least, we have to find gamma z theta. So 1 by 2. So z does not depend upon theta. So the first term will become 0. Also, u theta does not, uz does not depend upon theta. So the first term is 0. U theta does not depend upon z. So the second term is 0. So epsilon z theta is 0. So gamma z theta is 2 times epsilon z theta. And it turns out that shear strain z theta is 0. Okay. Though they had asked you epsilon theta theta, we have solved for all the strains. So if somebody tells you that what are the strains in the body, so these 6 things, they will constitute these strains. Okay. Do not write epsilon r theta as a strain. Epsilon r theta is 1 by 2 times gamma r theta. Your shear strain is actually gamma r theta. Keep this in mind. This way, I think question number 7. This was question number 7. This is from the same PDF which is available on professor's website. From there only I'm taking these questions. Okay, so question number 8 is state whether true or false. False. Epsilon equal to 1 by 2 gradient of u plus gradient of u transpose can be applied for cylindrical system, coordinate system also. So this is true because this is a generic mathematical formula. We just need to know how to substitute the gradient here. So this is true. For isotropic material, stress equilibrium equation in terms of stress components has the same form in both cylindrical and Cartesian coordinate system. This is not true. The component of strain matrix have the same mathematical form in both cylindrical and Cartesian coordinate system. This is also not true. Stress strain relation in all coordinate systems have the same mathematical form. True. Because in isotropic material, it doesn't matter in which direction you are moving. As long as those 3 directions are perpendicular to each other, it will work. So what is the formula for shear strain between radial and circumferential line element? So they basically want you to state the formula of gamma r theta. Okay, so we have already derived it. So 2 times this quantity will be gamma r theta. So it will be 1 by r del u r del theta minus u theta plus del u theta del r. So is there any option like that? This is the option. And question number 11, they have given you that think of a displacement in the body such that u theta equal to k, where k is a constant, and uz equal to 0. How much would be shear strain between radial and circumferential element? So basically, they want you to put the displacements in this formula. Now let's see if something will survive. So r is 0. So this term is 0. Del u theta by del r will be 0, but there is minus u theta by r term there. So the answer will be C, minus k by r. Okay. Then lecture 18. Question number 4. Which of the following is correct traction vector on positive theta plane in case of cylindrical coordinate system? Okay. So the answer will be okay. Z theta should act along EZ direction. R theta should act along ER direction, positive ER direction, because we are thinking about positive theta plane. And sigma theta should act along E theta direction. So the answer is A. For non-accelerating body with zero body forces, the correct expression of equilibrium equation in theta direction is. So they have given you that b theta equal to 0 and a theta equal to 0. Non-accelerating means a theta is 0. Basically here a theta, ar and az all are 0 because the body is non-accelerating. And the body forces are 0. This means that br, b theta and bz, they are also 0. But they in this question, they have asked you that what will be the equilibrium equation in theta direction. So we move on to our equilibrium equation. So this is the equilibrium equation in theta direction. They have told that b theta and a theta is 0. Okay. So what should be the answer? So the answer is C. Oh, wait. Actually, here there should be one del tau theta z by del z. So the answer will be D. Okay. So this is the answer. Question number 6. The approximate method where we assume that traction does not vary over the plane gives us the same linear momentum balance relations as the original analysis of the cylindrical coordinate system. Why does this happen? Okay. So the options are because traction does not actually vary over the planes. So this is not true. We are assuming that it is not varying. Okay. Because terms that arise due to variation of traction over the planes cancel due to excess symmetry. No, this is also not true. The option C is because the terms that arise due to variation of traction over the planes vanish faster when we swing the keyboard. Okay, so this is true because O of delta V, we have small o. The terms which we have, they're of the order of delta V. So when we shrink the volume, they will vanish faster than other terms. That's why this was this approximation was correct. Okay. Then lecture 17, the questions are consider the following statements. Statement 1, the partial derivative of ER with respect to theta is E theta. So this is true. The partial derivative of E theta with respect to theta is ER. So this is not correct. So the answer is statement 1 is true, but statement 2 is false. You can see the relation I have given you somewhere. Here you can see the relation. Okay. Which of the following statement is true? Cylindrical coordinate system can be used only for cylindrical bodies. So the answer is C, because any coordinate system can be used for any body. But when you use cylindrical coordinate system for cylindrical body, it becomes easy to solve the problem. Similarly, when you use the Cartesian coordinate system for cuboid shaped body, it becomes easy to solve the problem. We can solve the problem by using any coordinate system. So the answer is C. Okay. Select whether true or false. Basis vectors ER and E theta in cylindrical coordinate system are always perpendicular to each other. True. The third basis vector Ez is aligned along the axis and need not be perpendicular to other two basis vectors. This is false because in our assumption we have assumed that all three axes are perpendicular to each other. Which of the following statements are true regarding partial derivative of basis vector? Okay, so the partial derivative of basis vector ER and EZ with respect to R and Z respectively are always 0. So only option A is correct. because we are assuming that ER in our coordinate system, actually, we can see that ER, E theta, and EZ, they vary only with respect to theta. EZ is even independent of theta. So the only option A is correct. So these were some few objective questions which we have touched. I will take a short break of 5 minutes. And after that, we will move on to some subjective problems and we'll try to solve them. OK. So let's take a break of 5 minutes. If any one of you has any doubt, you can speak. You can write in the group. Sorry, you can write in the chat. And I will cater to your doubts after the break. Hello all. So welcome back to the lecture. So we will do some subjective questions also now. So the question is, verify verify that following stress field satisfies the Z equation of equilibrium in the absence of body force. And they have given you sigma RR equal to A times Z by R cube minus 3R square Z by R to the power 5. Sigma theta theta equal to AZ by capital R cube. Sigma ZZ equal to minus A times Z by R cube plus TZ cube by R to the power 5. They've given you tau RZ. They've given you tau RZ equal to minus A R by R cube plus 3Z square R by R to the power 5. Okay. And they've given you tau R theta equal to 0, tau Z theta equal to 0. So first step should be what they have asked in the question. They have asked that what is the so first you should know the Z equilibrium equation. So the Z equilibrium equation is what? Tau ZR del R plus 1 by R del tau Z theta upon del theta plus tau ZR upon R plus del sigma ZZ upon del Z plus rho BZ equal to rho A Z. Okay. So they're given del, this is 0, and they want this equation to be, let us assume that non-accelerating condition is given. Non-accelerating condition is given. This means that AZ is also 0. Now, if you look at this equation, tau Z theta has been given as 0. So this term will vanish. So basically, we have to see if del tau ZR. Okay, one more thing is given that the relation between R, small r, and Z is given as capital R square equal to small r square plus Z square. Okay. So basically, we have to see if this relation is getting satisfied or not. Okay. So let's put everything here. So del tau Z upon del R will be what? This will be minus A differentiation of this is R actually. So maybe I should follow the similar. Sorry, keep this. So 1 by r cube plus r divided by so what I'm doing, I'm just differentiating this with respect to small r. So basically I need del r by, so let's calculate del r by del small r. This will be 2 times r and del r by del z will be 2 times z. Okay. So let's substitute del r by del r in this equation. So del tau zr divided by, sorry, differentiated with respect to r will be minus a 1 by r cube minus 3r r to the power 4 into 2r. I made a mistake here actually. So basically, if you differentiate this capital R, you will get 2R. So from here, we will get del R upon del R as small r upon capital R. Okay. Similarly, we will get del R upon del Z as Z upon capital R. So here the replacement will be small r upon capital R plus 3z square upon r to the power 5 minus 15 z square r upon r to the power 6 to r upon r. So basically we have L tau zr upon del r as minus a 1 by r cube minus 3r square by r to the power 5 plus 3z square by r to the power 5 plus, sorry, minus 15 z square small r square by r to the power 7. We have del sigma zz upon del z. So del sigma zz upon del z. This will be what? So this will be minus a times. So I'm basically differentiating this. Maybe I should copy it somewhere so that it will be easily available for me. So we are basically differentiating sigma zz with respect to z. Okay, so this is the expression for sigma zz. So 1 by r cube plus z into minus 3 r to the power minus 4 del r upon del z plus 9z square r to the power 5 plus so if we replace del r by del z by z by r, which we have already calculated here, so we will get what? 3z square upon r to the power 5 plus these two will cancel. So actually we will get 6z square minus 15z to the power 4 upon r to the power 7. So this is what we will get. So let's simplify it slightly. And there is one other term also, tau zr upon r. This also. So from here we know that tau zr upon r is what? Minus a 1 by r cube plus 3z square by r to the power 5. Okay. So let's put everything together. So here we have 1 by r cube, here we have 1 by r cube, here we have 1 by r cube. So we have 3 by r cube here. Okay. Now from here and here we have 3z square by r to the power 5. So we have total 6z square upon r to the power 5. Okay. Minus from here we have 3 r square r to the power 5. And here we have minus 3z square r to the power 5. Please. Okay, so we are left with 15z square r square upon r to the power 7 minus 15 z to the power 4 and r upon 7. Okay. So if we club these two, what we will get? We will get minus a 3 upon r cube plus 6z square r to the power 5 plus minus 6 r square by r to the power 5 minus, if we take 15z square by r to the power 5 common, sorry, r to the power 7 common. What we will have here? We will have r square plus z square. Okay. So here should be 3. Here also what happened? R square plus z square became capital R. So these two cancelled. I think I made some mistake somewhere. Anyways, so let's calculate further. So we have minus a 6z square upon r to the power 5 minus 15z square. Here this has become capital R square and it will be replaced by this. These two will cancel and this will have r to the power 5. So basically we are left with what? 9z square r to the power 5. So I suppose I have not made any mistake in the calculations. And after calculating, if we are getting a non-zero value, this is not equal to 0. This means that Z equilibrium equation is not satisfied. Okay, not satisfied. Now suppose if there was some calculation mistake here, and if you later find out that this term actually cancel, this becomes 0, then the Z equilibrium equation is satisfied. So this question was basically just to show you what is the procedure to conclude something. And I hope you will retry it at your home. And let's see if you find any bug in the solution. Anyways, now let's move on to other question. So the question is, again, you are given with different so you are given sigma RR, sigma ZZ, tau RZ, and you are given sigma theta theta as 0, tau R theta is 0, and tau Z theta equal to 0. You are again given R square equal to Z square plus small r square. And they're asking that they're telling you that assume body force is absent. Okay. This means BR equal to B theta equal to BZ equal to 0. And they're also telling that body is non-accelerating condition. Okay. Non-accelerating. Now, the funny thing about non-accelerating is the body can be in constant velocity. It can be moving with a constant velocity, but it is not accelerating. So that's why AR A theta and AZ is also 0. And they're asking, will this state of stress satisfy the equilibrium condition? Now, there is one thing I'd like to highlight in this question. You can see that the sigma theta, tau r theta, and tau z theta, they are 0 actually. This means that this is a plane stress condition in r theta z coordinate system. So again, we will follow the similar procedure. Last time we did it for uh, the z equilibrium equation only. In this case, we will have to check other equilibrium equations. Okay. Now, first, del r upon del small r is small r by r as calculated in last question. Okay. Del r upon del z is z upon r. Okay. So this is what we have calculated earlier. Now you need to find the differentiations of these stress components so that we can check if they are like these are satisfying the equilibrium equation or not. So in our direction, the equation is this is already 0. This is 0. This is given 0 in the question. This is 0. So we are left with del sigma rr upon del r plus del tau rz upon del z plus sigma rr upon r equal to 0. Okay, so this is first condition which should be satisfied. So let's copy this again. So let's find del sigma rr upon del r is what? So I'm basically putting this here and differentiating 5r okay, And sigma RR upon R is minus 3p Z upon 2 pi R to the power 5. Now we will have to substitute all those in this equation. And we can take minus 3p by 2 pi as common. So from first equation, we will have Z upon R to the power 5 minus 5Z R square by R to the power 7. From second equation, we will have plus 2Z by R to the power 5 minus 5Z cube by R to the power 7. There will be one R multiplied here. Okay. And from third equation, we will have plus Z upon R to the power. So actually here it was 3pz R cube. No, sorry, R square. Made a mistake while giving you the number. So here it should be R square. So there will be some changes. Like here, when we are differentiating with respect to R, we will have one 2R present here. Okay. Here we will have 5R square. Okay. Again, here one R will be present. So let's write it again. So we are taking 3p by 2 pi common, so 2zr times zr should be r cube. Two zr, okay. Z cube r, okay. And it should be zr. So we have 3 times zr on 7 minus we take 5 zr upon z r to the power 7 common. So we will have r square plus z square from here. Plus from here we have 2zr by r to the power 5. Okay. So actually we can club this one also here. So it will be actually 5zr upon r to the power 5. Now this we can replace by capital R square. Okay. So what will happen? We have put all these three here. So this is our equation. So we are getting minus 3p by 2 pi into 5zr upon r to the power 7 minus here, sorry, r to the power 5 plus 7. Why am I writing as plus 7? Minus from here also you will get the same number but with a negative sign. So we are getting 0. Okay. So the equilibrium equation in r direction is getting satisfied. So The equilibrium equation in R direction is getting satisfied. Now we need to check if we are getting, if our equilibrium equation in Z direction is getting satisfied or not. Okay. So for Z equation, del tau ZR upon del R plus 1 by R del tau Z theta upon del theta plus tau ZR upon R plus del sigma ZZ upon del Z plus rho BZ or BZ, whatever you prefer, 0. So here these are 0, this is 0. So we are left with okay. Okay, so let's substitute here. Del sigma ZZ upon del Z equal to just give me 1 minute. Actually, my laptop has gotten some problem. I will just take a screenshot. So del sigma ZZ upon del Z will be what? Minus 3p by 2 pi is common. 3z square upon r to the power 5 plus z cube into minus 5 r to the power minus 6 into del r upon del z. Okay. So this is minus 3p by 2 pi into 3z square upon r to the power 5 minus 5z to the power 4 by r to the power 7. Okay. Tau rz upon del r is minus 3p z square by 2 pi. We can take this as common. So this is 1 by r to the power 5 minus 5 small r to the power minus 6 del r upon small del r. And we have tau rz upon r. Okay. This is minus 3pz square upon 2 pi r to the power 5. So we will substitute this, all this here in this equation. Let's say this equation is A. We will substitute all these in equation A. So first this part is there. So we take minus 3p by 2 pi common because that is common in everything. Z square by r to the power 5 minus 5 r square z square upon r to the power 7 plus from here we are getting 3z square upon r to the power 5. Okay. Minus 5z power 4 r to the power 7. And from here we are getting z square upon r to the power 5. Okay. So we can club these three. We can club these three. And we can club these two. Okay. We can club these two. So what we will get, write it here. So we will get minus 3p upon 2 pi into 5z square upon r to the power 5 minus 5z square upon r to the power 7 into r square plus z square. Okay. So this we can replace by, this is same as r capital R square. So finally we have minus 3p by 2 pi into 5z square upon r to the power 5 minus 5z square upon r to the power 5. So these two cancel and we get 0. So what can we conclude? Equilibrium equation along z direction is getting satisfied. Z direction is getting satisfied. Okay. So what did we do? We first found out that, okay, what do we have in our hand? Like we were given BR, AR and all those things. Depending upon we, so generally in these kind of questions, the steps will be same. Either you will be given a full-fledged 3D displacement and they will ask you to calculate the epsilon or what will be the shear strain, or they will give you like the expressions of sigma and they will ask if it is getting, if it is satisfying the equilibrium equation or not. Or there can be like they can give you the constitutive relation, like they will tell you that this is the isotopic body, these are the strains, and and uh, these are the strains, and please find the stress components. Okay, they will tell you to find 6 stress components. So the questions will be like that. I have already like given you the objective type question, like and how to deal with them. These things will be available on the Google Drive I have shared, and so that was pretty much what I wanted to cover. Maybe I will give you a hint for this problem. So question number 2 from lecture number 18. Question 2 from lecture 18. Okay. Objective. Question 2, lecture 18. So where was I? So they're telling that deduce the radial theta and axial component of divergence of stress tensor. Okay. You may use the following definition of divergence in cylindrical coordinate system. So So the trick which I want you to use is that divergence of, if somebody tells you to calculate the divergence of a matrix, okay. Suppose it tells you, suppose there is a stress tensor and they're telling you to calculate the divergence of matrix. This means that you need to calculate the trace of this matrix. If you do this, you will be able to find the solution. Other thing is you can use this formula. You can put everything here. And when you put everything here, you will realize that at the end, you will be getting the same thing, which I have told you. Try it by using both the methods. Okay. There is one other question in lecture 19. So for this, uh, I'm just giving you a hint in question number 1 from lecture 19 that of course you have to use this formula of gradient, but you have to keep in mind that E theta, ER and E phi, they will be different. Okay. They will not be constant in a spherical coordinate system. So while finding the gradient, while finding the strain matrix, you will have to first calculate gradient of U. And that gradient of U, and you have to write U in a spherical coordinate system. Like for cylindrical coordinate system, we wrote it in cylindrical coordinate system, right? UR, ER plus U theta, E theta plus UZ, EZ. In this case, you will write in spherical coordinate system. You will substitute your U in place of F here. And then you have to keep in mind that E theta, ER and E phi, they might be depending upon R, phi or theta. So you will have to do some mathematics, like what will be del ER by del R, what will be del E phi by del R, what will be del E theta by del R. Okay. And after doing that mathematics, you have to just follow the steps we have followed for cylindrical coordinate system. If you do that, you will be able to find what is gradient of U. After that, once you have found out what is gradient of U, you can use the formula, this formula. This is a generic formula. Epsilon equal to 1 by 2 gradient of U plus gradient of U transpose. Okay, use this formula. You will be able to find what is the strain matrix in a spherical coordinate system. But the key thing is you should be able to understand that you will write U in a spherical coordinate system. You will have to find the differentiation of basis vectors with respect to coordinate systems. If you do these things, you will be able to solve this problem. I hope I have made myself clear. If you have any doubt, you can ask. Otherwise, I will end the meeting. If anyone has any doubt, they can ask right now. Anybody has any doubt? Okay, you can write in the chat also. You can unmute yourself. You can. Okay, so anyways, if none of you have any doubt, then I will end this meeting. So I'm Manoj Shikhar. I take sessions on Tuesdays from 6 to 8 p.m. And I'm one of the TAs in this solid mechanics course. And if you have any doubt related to my session, you can post your doubts on the Swayam portal, on the discussion forum on the Swayam portal. I will try to clarify your doubts there also. And let's meet all of you in next week. Thanks a lot. Bye bye. Anybody has any doubt? Because I will be leaving now. Okay then. Bye.